Let's say we have a very long wire shaped like this, like long wire stretching out in this direction, long wire stretching out in this direction, and let's say it's connected by a resistor, maybe a light bulb, maybe a buzzer, is some sort of resistor connecting them together. And let's say there's also a magnetic field. Let's say the magnetic field is, let's say, in the inwards direction. And let's say we know the strength of the magnetic field. Let's say it's, I don't know, 4 Teslas everywhere. So a uniform magnetic field, 4 Teslas inwards everywhere. Do we currently have a complete loop here? Do we have a complete circuit? No, no complete circuit. We've got most of the circuit, but these don't actually connect. So let's say we do connect them by taking a metal bar and just placing that metal bar across the wires. That forms a complete loop now. Essentially, we're forming a short circuit, or not exactly a short circuit, just completing the circuit. But the important thing about having a metal bar here is we can slide it around. And why would it be useful to be sliding this around back and forth, or one way or the other? If we move this bar, what happens? Yeah, that's changing the flux by changing the area, exactly. The flux here, let me just draw in an example location. Let's say right now the bar is right here. And let me label some dimensions here as well, because if we're talking about flux, how do we define flux in this case? How would you calculate flux in a case like this? Like what formula would we use? Yeah, magnetic field times area times cosine of the angle. ABC, area times magnetic field times cosine of the angle. Because we definitely have an area. There's an area enclosed within this loop of wire. There's a magnetic field in that region. And as for the angle, the theta here is supposed to be the angle between what and what? How do we measure the angle? Yeah, the angle between a normal vector and the magnetic field. So the normal vector is going to be a vector perpendicular to the surface. So what are our options for the direction of the normal vector here? If we've got this surface, what possible directions would be perpendicular to that? Yeah, either outwards or inwards. So we have the option of choosing an outwards normal vector or an inwards normal vector. Either one will work mathematically, but I find that it's a lot easier to understand what's going on if you choose the one that most closely agrees with the existing magnetic field. In this case, since the magnetic field is inwards, I would choose inwards as the direction of the normal vector. So that's, let's say, n, the normal vector. So this normal vector pointing inwards, and that's basically just a reference for direction. That we're talking about the angle between that normal vector and the magnetic field vectors. And what would that angle be in this case? What's the angle between the inwards magnetic field and the inwards normal vector? Yeah, angle is 0 degrees. So we've got cosine of 0 degrees, which is therefore just going to be 1. So in this case, the magnetic field is just area times magnetic, or sorry, the magnetic flux is just area times magnetic field, because cosine of 0 degrees is 1. And is that value changing as time passes here? What's causing that value to change if it's changing? Yeah, the area is changing. If we move this bar to the right, the area is increasing, or if we move it to the left, the area is decreasing. So magnetic field is staying constant, but the area is changing. And so the fact that the area is changing means that the flux is changing, and changing flux means what's going to happen. What should we expect if the flux is changing as time passes? Yeah, we're going to get voltage. We get this extra voltage boost, almost like there's a tiny invisible battery in the circuit, because the flux is changing. And this goes back to Lenz's law and or Faraday's law. That you get an extra voltage, the induced voltage, sometimes called epsilon induced, but it really is just a voltage difference, an extra boost in voltage, equal to negative rate of change in flux, d flux dt. So if we can calculate the derivative of this, that'll tell us how much voltage we get. The very fact that this is changing as time passes means we will get a voltage. If we can find the derivative of this, that'll tell us how much voltage. And also the negative sign gives us some information about direction. Any questions on that so far? So let's try this out. We've got magnetic field is just this constant 4 Teslas everywhere. How would you write out the area enclosed within this loop though? Geometrically, that's just a rectangle, right? How do you find the area of a rectangle? Yeah, length times width. So let's label those. Let's call this width x and this height y. So that means the area would just be x times y. So this area can be expanded into x times y. And we find that the flux is just going to be x times y times magnetic field. And if we want to know the rate of change in flux, we can just take the derivative of that. D flux over dt. Let me do some more in here, actually. So the induced voltage, epsilon induced, is negative. I'm going to ignore the negative for now because we're just looking at this in terms of magnitude. We can fill in the direction later based on that negative sign. But let's just say absolute value of induced voltage is absolute value of derivative of x times y times b. Looking at absolute value for now because we don't really care about direction yet. We'll look into direction later. But to find that, we're taking the derivative of x times y times b. Of those quantities, what's actually changing as time passes? Yeah, just x. As we move the bar, x is changing because x is the distance from the beginning to the location of the bar right now. So x is actually changing as time passes. But y, the distance between the wires, doesn't change, and b is 4 Teslas everywhere, so that doesn't change either. These are constants. What can you do with a constant multiplier in a derivative? Right, you can pull those out. Constant multipliers can be pulled out of a derivative. So we're left with just y times b times derivative of x. But x is a distance. X is the position of the bar. And what do we call the derivative of position with respect to time? Yeah, that's exactly the velocity, the speed at which the bar is traveling along this track. So this ends up being distance between wires times magnetic field times speed of the bar. This tells us exactly what voltage we're going to get. And so this suggests that the further apart the wires are, the more voltage we get. The stronger the magnetic field is, of course, the more voltage we get. And also, the faster we're pulling this bar along the track, the more voltage we get. But note that this only applies while we're in the process of moving the bar. As soon as you bring the bar to a complete stop, V is 0, so the extra voltage vanishes and you don't get any current flow. We can also figure out the current. Speaking of current, if you know the voltage in a loop with a resistor, how would you find the current? If you think back to 7b, when we were working with circuits, how would you figure out the current flowing through a resistor? Yeah, we can use Ohm's law that delta V equals negative IR. And I'm going to ignore the negative again here because that's just talking about direction. The resistor is really the only thing in this loop that uses voltage. So the resistor is getting that full voltage. This YBV, the induced voltage, is the voltage this resistor gets. So we can set those equal, divide by R, and that tells us the current. So the current that we should expect to flow through this loop is distance between the wires times the magnetic field strength times how fast the bar is being moved, divided by the resistance. That'll tell us the current through that resistor, which we can assume will be, will give us information about how bright the light bulb is, if it's a light bulb, or how loud it is, if it's a buzzer. Any questions on that so far? Now let's take a look at direction. So far, we haven't really talked much about which direction the bar is moving, but let's choose a direction and go with that. Let's say we are currently holding the bar and pulling it to the right. So let's say this is the velocity vector. The bar is moving to the right. So that means the flux is increasing or decreasing? Yeah, flux is increasing. As we move the bar to the right, the area is getting larger and larger. Area getting larger and larger, the magnetic field staying the same and angle not changing either means flux is increasing. Flux is increasing. And formally, flux is a scalar, not a vector. Flux does not have a direction, but it's often useful to treat flux as being associated with the direction of the normal vector we chose. So I would think of flux as, even though it's technically a scalar, I would think of flux as being in the direction of the normal vector, an inwards vector. So if you've got an inwards vector, because that's the normal vector we chose, and it's increasing, it's getting larger and larger and larger, that's a change in which direction? Yeah, that's a change in the inwards direction. An inwards vector that gets stronger and stronger and stronger is a change in the inwards direction. Delta flux is in the inwards direction. So going back to Faraday's law, the d flux dt would be considered an inwards vector. Not technically a vector, it is a scalar, but we can associate it with the inwards direction. But then we have the negative sign in Faraday's law. What does that suggest? Yeah, the negative sign just reverses that. So the change in flux is in the inwards direction. The negative sign in Faraday's law reverses that, so the overall result, the voltage, would be associated with the outwards direction. Of course, nothing's flowing outwards because that's not the direction the wire's pointing, but you can use the right-hand rule. Inwards change, reverse because of the negative sign, so point your thumb in that reverse direction, and the curl of your fingers of your right hand suggests the direction of the current. So current is going to flow in this direction. So we describe this in this case as counterclockwise. As the bar moves to the right, we get current flowing counterclockwise. And we can even calculate how fast that current is. That current will be distance between wires times 4 teslas, the strength of the magnetic field, times the speed of that bar, divided by the resistance of this light bulb or buzzer or whatever. Again, for the direction, you look at the change in flux. Flux is increasing. The normal vector we chose is inwards. So inwards and increasing is more and more inwards. Delta flux is associated with the inwards direction. Negative sign in Faraday's law says reverse that, so outwards. Point your thumb in the outwards direction. The curl of your fingers tells you the direction current is going to flow. So that's the direction of the induced current. Any questions on that so far? And one other thing to verify, I guess to verify this as one last step, that current flowing in a loop also creates what? Anytime you got current flowing in a loop, what does that cause? Yeah, that current flowing in a loop creates its own induced magnetic field. And you can use the right-hand rule variant for that as well. Curl the fingers of your right hand in the direction current is flowing around that loop, and your thumb should tell you the direction of the induced magnetic field in the middle. So this final induced current creates its own magnetic field, which is in a direction opposite to the change that created it in the first place. The induced current creates its own final magnetic field that's in a direction opposite to the change that caused it. Not necessarily opposite to the existing magnetic field, but opposite to the direction of change. Because that's really what this expression is all about. The final result is opposite to the direction of change. Any questions on that directionality so far? And we could also run this process in reverse. Let's say instead of moving the bar to the right, let's say we move the bar to the left instead. If the bar moves to the left, what's happening to flux? Yeah, if the bar is moving to the left, then the area is shrinking, so we get a decreasing flux. So if the bar moves to the left, flux is going to be decreasing. And if you've got an inwards vector that's getting weaker and weaker and weaker and weaker, that's a change in which direction? Right, an inwards vector getting weaker is a change in the outwards direction. So the change is going to be in the outwards direction. Again, the change in flux is technically a scalar, but we can associate it with that direction based on the normal vector. Normal vector is inward, but flux is decreasing, so that's a change in the outwards direction. Going back to the negative sign in Faraday's law, an outwards change with that negative sign becomes an inwards result. Inwards result suggests that the current is going to flow this way. So that would be clockwise around the loop when viewed from this perspective. So we get the exact opposite result. If we move the bar to the right, current's going to flow counterclockwise. If we move the bar to the left, current's going to flow clockwise. Any other questions on that so far? One other interesting result of this, if we focus on just the bar itself, if you take a look at the current in the bar, again, let's say we're back to the original situation of the bar moving to the right. So bar is moving to the right. We've got current flowing upwards in that bar. And of course, around the whole loop, it's circulating counterclockwise. But if we focus on just the bar, we've got charge flowing upwards in the presence of an inwards magnetic field. That's charge moving in the presence of a magnetic field. So what should that wire, that bar, experience? Anytime you've got current flowing in the presence of a magnetic field, Yeah, that's going to experience a force. And yes, it should be to the left based on the second right-hand rule. So using the 3-finger variation, you point your thumb in the direction charge is flowing, not the velocity of the bar. The velocity of the bar is pretty slow compared to the actual flow of current. The flow of current is the important thing here. So point your thumb in the direction of the flow of current, point your index finger in the direction of the magnetic field, straight into the board, and your middle finger tells you the direction of the force. Or alternatively, if you find it difficult to hold your fingers perpendicular, point your thumb in the direction of the current, your flat fingers straight in the direction of the magnetic field, and imagine a push from the palm of your hand. So that's a push to the left. This bar experiences a force to the left. Which means if this bar is just sliding to the right, but it experiences a magnetic force to the left, what's going to happen to it as time passes? What happens in general if you just got some object moving to the right, but experiences a force to the left? It's not so much that they cancel out exactly, because you wouldn't be adding these vectors. You can't add meters per second plus newtons. They're different quantities. But what would that force do to the object if you've got a force pointing in a direction opposite to the velocity vector? Like if an object is moving one way, but you're pulling on it in the other direction, yeah, it's going to decrease the velocity. The magnetic force acts to slow down the bar. And this really goes back to the meaning of this negative sign here. The negative sign means the end result acts in a direction opposite to the change that's causing it to happen in the first place. The change is the bar moving to the right. The end result involves a force pushing back to the left. It's acting to slow itself down. And this is ultimately conservation of energy. As the bar moves, it has kinetic energy, but the flow of current is converting that energy into other forms. For instance, if this is a light bulb, then energy is leaving the system as light and heat. You can even calculate how fast using any of the power equations from 7b. Power equals I squared R, for instance. So if energy is leaving the system, presumably this bar should be losing kinetic energy. So for instance, slowing down as a result of this force. So the force approach and the conservation of energy approach both agree that this bar should be slowing down as it moves. Unless, if you want this to maintain a constant speed, what would you have to do to it? How would you keep it from slowing down? How would you make sure it continues at a constant speed? Yeah, you've got to apply your own force to the right to balance out the natural magnetic force to the left. In order to keep this moving, prevent it from slowing down, you have to be pulling on it as it moves. You have to be applying your own external force on the bar to the right. And if you're applying a force on the bar as it moves, that's a force times a distance traveled. And what do we call that? Force times distance equals, yeah, from way back in 7a, that is work. If you're applying a force to this bar as it moves, you are doing work to the bar just to keep it moving at a constant speed. And work is a transfer of energy. So by pulling on this bar just to keep it moving at a constant speed, you're applying work. You're transmitting energy to the system. And where does that energy go? What happens to the energy you put into the system via work? What does that energy get converted into? It's not exactly potential energy in this case. It would be potential energy if we had a capacitor here instead of a light bulb. But yeah, if we've got a light bulb here, it's leaving as thermal energy as the light bulb gets warmer, and also as light. Or if we didn't really care about the temperature, we might just say it's leaving as heat. That you're doing work to the system by pulling on the bar, but light and heat are leaving the system, and that counts as an energy leaving the system. So this is basically a machine for turning work, your muscular work here, just by pulling on the bar with your arm, and turning that muscular work into light and heat leaving the system through a light bulb. So you're doing work to make the light bulb light up and get warmer. In fact, that's really what any generator is all about. This is a pretty simple example of a generator compared to most of the real world examples, but this is technically a generator. It's a device for turning mechanical work into electrical current, which you can then do something with. And this is generally the basic idea of how generators work. A generator is just some way of using a loop of wire and a magnetic field to turn mechanical work into electrical power, electrical current. Any questions on that so far? Mechanical work, yeah, changing flux specifically. We're not really changing the magnetic field. The magnetic field is just this constant 4 Teslas. But if we just grab this bar and start sliding it back and forth, we are doing work because you're applying a force to counteract the natural magnetic force. You're applying a force as the bar moves some distance. So you're doing work, and that work causes current to flow. So this is essentially a simple generator. If you're just pulling it at a constant speed in one direction, you're creating DC, direct current. It'll be the same current the whole time. Whereas if you slide it back and forth, you're creating alternating current. You get current flowing one way as you move the bar to the right and current flowing the other way as you move the bar to the left. So if you just drag this bar back and forth as an oscillation, you're going to oscillate between counterclockwise current and clockwise current every time you change directions. And at the instant when you come to a stop and change directions, at that instant, there's no current because you brought the speed to 0. And at that instant when speed is 0, because you're in the process of turning around, there's no current at that instant. Any other questions on that so far? And a more common example of a generator is involving a loop of wire that you're rotating in a magnetic field. Because having this approach where you're moving an object back and forth can be very inconvenient and not very efficient either. But if we take another approach where we take a loop of wire and rotate it, that leads to a different application of Faraday's law that looks rather different, but still leads to the same result of mechanical work turning into electrical current. So let's try this out. Let's say you have, let's say we've got an upwards magnetic field. And let's assume for simplicity it is a constant magnetic field. Let's say the same 4 Teslas everywhere, but straight up. And let's say we have a loop of wire that is horizontal. So a loop of wire held like this, horizontally. So let's say our arrangement looks something like this. And let's assume that this has a light bulb or something in it. I won't actually draw the light bulb in, but let's assume there is one. And we have this loop of wire. Is there currently flux involved here? Does there exist flux? No flux at all? Do we have field lines passing through the interior of this loop? Yeah, there is flux. If you've got this loop held horizontally and magnetic field straight up, the magnetic field is definitely passing through the interior of the loop. So there's actually a very large amount of flux here. But if I'm just holding this still, that flux doesn't lead to any any induced current, because induced current, induced voltage doesn't just require there to be flux, it requires what to be happening? Yeah, there's got to be a change in flux as time passes. Induced voltage and induced current happens when the magnetic flux is changing. And that's when it's currently in the process of changing, not just that it has changed at some point in the past. The magnetic flux has to be changing right this instant in order for there to be induced voltage. And the faster the flux is changing, the more voltage you get. So let's write out the flux here. We've got the usual formula, flux equals ABC, area times magnetic field times cosine theta. And of course, for the angle, we should choose a normal vector. Which direction would be useful to use as the normal vector here? Probably upwards, yeah. With a horizontal loop of wire, our options are straight up or straight down, because those would be perpendicular to the surface. And it's more convenient if you choose the one that agrees with the existing magnetic field. So let's say upwards is our normal vector. That's just a vector perpendicular to the surface enclosed inside the loop. Then right now, we've got an angle of 0, because the normal vector and the magnetic field agree with each other. They're in the same direction. So at this instant, we've got cosine 0, which is 1. So right now, flux is area times magnetic field times 1. But we could be changing that. Usually the way a generator works, most generator setups, is you take this loop of wire in the presence of a magnetic field and you start spinning it. Because if you spin this, let's say we rotate this way. So we've got a new orientation of the loop of wire. New orientation, which is going to mean we get a new normal vector. And now that the normal vector is pointing this way, we take our loop of wire with the normal vector and we tilt it. The normal vector is now pointing this way. And now there's a non-zero angle. There's now this angle, theta. So that means as we rotate, the area isn't changing because we're not stretching or compressing the loop. We're not moving any bars along tracks like we were earlier. The magnetic field is not changing. We've just got this same constant 4 Tesla upward everywhere. But the angle is changing. And the fact that the angle is in the process of changing means we do get a change in flux as time passes. And we can even figure out the rate of change here. We can calculate the derivative of flux. Again, if we take the derivative of this, in this formula, what counts as constants in this situation? Yeah, A and B are both constants, so we can pull those out of the derivative. And we're left with derivative of cosine. Anyone remember what derivative of cosine is? Yeah, it should be negative sine. Cosine and sine sort of repeat each other as you take derivatives. Derivative of sine is cosine. Derivative of cosine is negative sine. And you can see that from the graphs. If you graph sine theta and cosine theta right on top of each other, at any given instant, the value of sine tells you the rate of change of cosine and vice versa. And there is a negative there, but I'm going to ignore the negative because we're just looking at amount here. Let's ignore direction for the moment. So A times B times sine theta. And also because of the chain rule, we got to multiply by the derivative of what's inside, d theta dt. To maximize energy in a generator, would you have a loop that both increases and decreases in area? You could certainly combine these effects. You could have a situation where the area is changing and the angle is changing and the magnetic field is also changing. So you could have all three of these changing. But in a typical situation, we'd be focusing on just one of those changing and hold the other ones constant. Like in this case, we're assuming the loop of wire is rigid. It's not going to stretch and compress. All it's doing is rotating. But it's certainly possible to have more than one of these changing. It's just, and in that case, you would presumably use the product rule. When you take the derivative, let's say two things are changing, you take derivative of the first thing times the second thing as it is, plus derivative of the second thing times the first thing as it is. In this case, we're assuming A and B are constant, so those can just be pulled out. No product rule necessary. But cosine theta, when you take the derivative, becomes negative sine theta. Again, ignoring the negative, because that's just telling you about direction anyway. And then chain rule says take the derivative of what's inside also, d theta dt. But think back to physics 7b. What do we call the rate of change of angle? D theta dt. What else is that called? If you've got an angle changing as time passes, what do we call how fast the angle is changing? Yeah, that's the angular velocity. D theta dt is omega, the angular speed. And I'm going to call it just speed instead of velocity because at the moment we don't care about direction, just the fact that the angle is changing. And d phi dt tells you the induced voltage. So the amount of voltage you get depends on how big the loop is, how strong the magnetic field is, what the angle is right now, and how fast the angle is changing. So to get the most voltage, you want a large loop spinning quickly in the presence of a strong magnetic field. But also the amount of voltage you get oscillates as time passes because some angles lead to sine being large and some angles lead to sine being small. So you end up with if you imagine the angles changing at a constant rate, that means sine theta is going to be oscillating. Sometimes you get a large voltage, sometimes you get a small voltage, sometimes you get no voltage at all. But the voltage you get as time passes is going to be oscillating. So this naturally leads to AC current, alternating current. Alternating in the sense that if you make a graph of time versus voltage, you're going to get a sine wave. Sometimes you get large voltage in one direction, then no voltage at all, then large voltage in the opposite direction, then no voltage at all. The amount of voltage you get and even the direction of the push oscillates as time passes. So a generator like this involving a spinning loop naturally produces AC current instead of DC. So this is why the voltage you get from a generator tends to be AC as opposed to the voltage you get from a battery, which tends to be DC. Any questions on that so far? So that gives us how much voltage, and then to get how much current, you would divide that by resistance as before. But let's see if we can figure out the direction. Let's say we started off in this orientation, and we start to rotate this loop this way. So I guess you could say you're rotating counterclockwise from this perspective. If you rotate in this direction, so let me just draw that out as initial and then final. And final not in the sense that we're stopping, but final in the sense of a little bit later. And we've drawn the normal vectors, normal vector, normal vector. And if we take a look at flux, as we go from this normal vector to this normal vector, is that going to involve an increase or decrease in the flux? Yeah, that should be a decrease. And you can see that kind of conceptually by the fact that as you rotate, you're now going to have fewer field lines passing through the interior. But also in terms of the A, B cosine theta, A and B are staying the same, so we don't need to worry about those. But if you take a look at the angles involved between the magnetic field and the normal vector, at the beginning, the angle was 0. Cosine of 0 is 1, which is the largest it can be. But if you change the angle, that angle is now something more than 0. So cosine of that angle more than 0 is going to be less than 1. So cosine theta has decreased as theta increases beyond 0. This is going to be a slightly smaller flux. So we're going from largest the flux can possibly be to a little bit less than that. Flux has decreased. And now let's go back to the idea of Faraday's law, that the induced voltage, the direction of that effect is negative d flux over dt, with that negative again signifying an opposite direction. Again, flux is technically a scalar. It doesn't really have a direction, but we can associate it with the direction of the normal vector. So normal vector at this initial instant is straight up. We've got a decrease in flux. If you've got an upwards direction and it's decreasing, that's a change in which direction? If a quantity, yeah, if you think of a quantity as upwards, but it's decreasing, that's a change in the downwards direction. So d flux dt is associated with the downwards direction. The negative sign says reverse that, and then use the right-hand rule. Downwards change, reversed, becomes an upwards overall effect. And upwards means current flowing this way. So I would call that counterclockwise when viewed from above. This loop, as we start to tilt it, is going to experience induced current in a direction counterclockwise when viewed from above. So that's going to look like current flowing this way. That will be the current flowing counterclockwise when viewed from above. Or if you rotated it the other direction, you'd have the opposite effect. Or would we? Actually, if you rotate it the other direction, let's say you rotate it this way. What's going to happen to flux? Would flux be increasing or decreasing? Yeah, if you start here and rotate the other direction, that's also a decrease in flux. Because when it's held level like this, when the loop of wire is held exactly horizontal in the presence of a vertical magnetic field, this loop right now is the maximum possible flux. Rotating it in either direction is going to involve a decrease in flux. So tilting it one way leads to current flowing counterclockwise when viewed from above. Rotating it the other way also leads to current flowing counterclockwise when viewed from above, because both of those tilts would involve a decrease in flux. If you want current flowing the other direction, you'd have to start at some other angle and rotate approaching that horizontal. In a full rotation, yeah, the problem with a full rotation is that it flips the normal vector around. So at that point, you would basically have to treat the angle as 180 degrees. And what's cosine of 180 degrees? Yeah, cosine of 180 degrees becomes -1. So when the angle goes to more than 90 degrees, you get a negative value for flux. And at that point, whether it's increasing or decreasing becomes really confusing. So what I would usually do is look at it just one small piece at a time. Investigate one small change at a time. And in each situation, choose the normal vector. And remember, you've always got two options for normal vector. For each little bit of change, choose the normal vector that most closely aligns with the existing magnetic field. And that makes it much easier to visualize what's going on. Any other questions on that? All right, then I will see you next time. You're welcome.